Hi, and this is the Physics High podcast. A quick quiz. Do you A, want to be inspired by science communicators? B, want to learn all about science education? C, want guidance on your scientific journey? Well, how about D, all of the above? Today, my guest is Dr. Luke Barnes. Now, Luke Barnes is based at the Western Sydney University, and his research area is particular of interest is the cosmic evolution of matter, also galaxy formation, and the fine-tuning of the universe in respect to life. Now, apart from his work, he's also authored two books. The first is The Fortunate Universe, which is about the fine-tuning argument, and the second, which is this one, The Cosmic Revolutionary Handbook, is all about the Big Bang, and both he co-wrote with Professor Geraint Lewis from the University of Sydney, who you may have already heard before in my previous podcast. But apart from his research and his writing books, he's an avid science communicator. Apart from not only teaching his students at the university, he loves sharing his knowledge of astrophysics and cosmology to the general public and also even to high school students, where I personally have experienced that, where he's visited a number of our classes at my school, sharing his expertise in astrophysics. So, welcome, Luke.
Thanks for having me.
Now, Luke, that's a brief introduction to you in terms of what you do, but really share us a little bit about your scientific journey in terms of what you do.
Yeah, so at the moment, in my point in a career, I'm employed as a lecturer. So my job is sort of basically half and half research and teaching. Before this, I was so if you want to become a researcher in sort of any scientific field, you need to get a PhD, which is kind of your apprenticeship. So I did mine in England at the University of Cambridge. And then you go on to what are called postdoc positions, which are temporary positions. So I had one of those in Switzerland at the Swiss Federal Institute of Technology, and then one at the University of Sydney, and then two fellowships where it's the same sort of deal, except I applied for the grant myself instead of going on someone else's grant, so I got to do what I wanted. So I had a grant at the University of Sydney and then one at Western Sydney University, where I am now. So it's great being a postdoc. It's not great because it's not permanent, which is always a bit of a worry, but it's very nice to just be able to focus completely on research. And at the moment, I'm getting in deep. At the moment, here we are, less than a month out from the start of semester, getting ready to teach.
Now, your particular area of expertise, as I stated before, was galaxy formation and also the evolution of matter. Can you tell us a little bit what that involves?
Yeah, so we see in the universe around us, how is the stuff arranged? It's not just spread out at random. Even stars aren't just thrown around at random. There's a structure at the universe on many levels. So we see stars surrounded by planetary systems. We see stars collected together into galaxies. So apparently, for some reason, stars like to get together in groups of, 1 billion up to 1 trillion-ish, with some smaller ones and some bigger ones. And then galaxies like to get together into groups. So our galaxy is part of the Milky Way, is part of the local group of galaxies with about 60 other galaxies, most of them much smaller than us. And then there are clusters of galaxies, which are even bigger, thousands of galaxies, and then clusters of clusters, superclusters. There's sort of structure on all these levels. And yet when we look back to the very early universe in what's called the cosmic microwave background, we can see back to when the universe was very young, and it was almost perfectly smooth. There wasn't this structure within structure. It was like the air in this room. There's as much air here as there is over here. How one turned into the other is the big picture of which I've sort of done my little bit to try and understand what's going on there in a couple of different ways.
Now, is it fair to say that in many respects, astrophysics and cosmology is still very much a vast unknown? I mean, you may get someone saying, oh, look, we know all about galaxies. I've seen pictures in textbooks. Surely there isn't much more to learn about them. And we know the physics behind it and, particularly in terms of how gravity works and so forth. How would you answer that? Is it a sort of the thing like we're only scraping the surface of our understanding of the cosmos?
Well, here's one way here's one way to put it. I think we know what the characters are and the rough outlines of the plot. but it's a little bit hard to know how they all interact with each other. So, of course, gravity is going to play an enormous role, probably the major role in the universe. So wherever there's a lump of stuff in the universe that's a bit more dense than average, because of its gravitational pull, it will pull things in. And so, the rich get richer, the lumpy get lumpier, and structure forms in that way. But we see a lot of very detailed properties and correlations in galaxies. We see that some of them are very flat disks. The Milky Way is one of these, where the stars are going around in orbits around the center in a nice flat disk. But we also see galaxies which are more like a ball of stars, sort of randomly all swarming around, with no real sign of any coherent, rotation, motion, or orbits or anything like that. We see even within disk galaxies, we see that they often have a bulge at the center, as if there's sort of, as well as the disk, someone put an extra bit in the middle there. We see in our galaxy evidence of both a thin disk of galaxies, which is very sort of sharp and thin, and then a thicker disk, which is kind of puffed up. We also see streams of stars, where the best idea we have is that some galaxy has fallen into the Milky Way and been sort of ripped apart as it went around. So the problem is, there's this thing in astronomy where, the more detail you have, it's on all of science, I guess, the more detail you have, the harder it is to understand what's going on. And so actually Geraint, who you mentioned before, my colleague, told me when I was his sort of student that, the problem with studying the sun as an astronomer is it's so close and so well studied that any idea you have is already wrong before you get it out. Whereas if you have some idea about really, really distant, far away galaxies, it's just a blob. It's just some smudge on someone's observation. So you can't be proved wrong yet. But I mean, we have so many galaxies and such detailed now, data about, especially our galaxies, our local group and the ones around us, and pushing further out into the universe, that there's a lot of correlations we need to explain.
What drives you? I mean, what is the thing that makes your current work so interesting for you?
So there's a lovely quote by a guy called Ed Hines, which is just an old New Scientist, which basically says the universe is the biggest jumbo crossword puzzle you've ever seen. That it's all interconnected, and there's some answers in there somewhere, but it's not going to give them up, for free. You've got to go searching for them. And so the universe sort of presents itself to us as this puzzle for us to solve. And there's a couple of things that sort of draw you in if you're a physicist. One of them is if you're good at maths, then seeing that sort of writ large across the universe, and then down in physics in the smaller stuff like atoms and molecules and all that, is kind of amazing. It's not just that our universe is mathematical, but the mathematics that it uses is some of the most beautiful mathematics we've discovered. So it sort of, the universe looked at all the options of the maths it could have used and picked all the good stuff, went for the top shelf of all the beautiful ideas. So for me, it's especially, I'm a theorist. So my job is really in the equations and simulations on the computer, not so much taking in the data or analyzing the data, but trying to understand why it is what it is. And so being able to bring together the different laws of nature that we know to try and understand what's happening out there in the universe is part of that great puzzle.
I assume, you got into science obviously quite early. Surely you were interested in science when you were a lot younger. Was there something seminal, a moment that got you into science, or was it a growing realization? Tell us a little bit about your journey as to how you got to where you are.
So I was kind of a dinosaur nerd as a kid, to be honest. I mean, it's no great surprise that I was some sort of nerd as a kid. I think really at year 11 and 12, doing physics and seeing how applicable mathematics was. So I was always good at maths. That can't be a surprise. I'm a theoretical astrophysicist now. But, all those sort of made up problems you find in math textbooks and and being able to do that was all great. But having sort of the problems present themselves in the real world, and you really being able to solve something about the real world, is an amazing discovery. There's a book by Paul Davis. Says that when he was in high school, he was sitting down doing a physics assignment, and it was, a cannon shoots a cannonball at 45 degrees up a slope that's at 30 degrees, something like that. Where does the cannonball land? And while he's doing it on pen and paper, a girl who he happens to like comes up and asks him what he's doing, and he sort of explains the problem. And she says, "How can you know what the world is going to do by writing things on a piece of paper?" And Davis says, a career and, probably 20 scientific books later, he still doesn't have a good answer to that question, but it's an amazing thing.
Now, you see, I assume, apart from being a theorist, you see yourself also, I hope, as a scientific communicator. The importance of communicating science, and in fact, as you shared with me earlier, your first year course is actually about scientific literacy to your students in the first year. How important do you see your role in terms of communicating science?
So I think there are probably other disciplines where it's sort of crucial to the human race. If you're a climate scientist or something, or a medical scientist, and you've discovered something, you've got to get out there and tell people. As an astronomer, it's not quite that urgent, but there's still a couple of reasons why I think it's extremely important. One of them is that space and astronomy are kind of gateways into science. So an awful lot of people who are scientists today, or in technology today, or engineers today, it was the space race that got them interested in science, and then whether they went into astronomy or something else, that was their doorway in. And so I think that's quite important. Unlike maybe a lot of some other fields, you can give an astronomy talk to kindergartners and people at any age, and if you do it right, you'll hold the whole room there. So I think it's important for people to sort of understand. I think those sorts of things, they can just be enjoyable. Like, people should enjoy just learning stuff about the universe. But I think there's also, and this was one of the reasons Geraint and I wrote the book. Nope, that one.
That one
is we really wanted to sort of look at why scientists believe what they believe. So, and I think there was a lot of cosmology books that I certainly read. There's a bunch behind me. I still like reading them. But they sort of presented the wild and wacky out there ideas in cosmology. And that's all great. But I think there's another story you've got to tell where you say, okay, let's strip it back to the bare evidence and say, all right, what are the non-negotiables here? What have we seen in the universe that leads us to the theories that we have? So I think that's quite important as well in terms of communicating. And, people just enjoy understanding stuff. And I think if you can create a bit of that going around, then I think that leads them to appreciate science. At the very least, it gives people an idea that if they're going to disagree with science, they'd better, get their act together and actually disagree with the evidence they present.
That basically touches on an important concept, that it's not just about communicating science and doing awe-inspiring stuff. Astrophysics, astronomy does that. But as you do in your book, in terms of the Cosmic Revolutionary Handbook, scientific literacy is very important, and clearly it is important at the university level. Tell me, why is the university offering courses, and that you are running, on scientific literacy to science students?
I think one of the important things is that students, when they need to be able to, if we have a science student, they need to be able to write as a scientist and speak as a scientist. And that's a slightly different thing to other sort of writing and speaking that they might have done before. So if they're anything like me, in year 9 English, you got given a book that maybe you wanted to read, maybe you didn't. And then you got into the exam and they asked you some question and you were like, how do I go on about this for 6 pages? And so you knew this much and you were trying to write 3 times or 4 times as much by, whatever devious methods you could. That one of the things we need to teach them is to say, all right, that's not going to be the situation you're in. You're going to have something interesting that and something that might even be important to say to a lot of people, and have them at least not just straight out believe you, but evaluate you and take you seriously. And you're going to need to try and write that down and try to say that. And you're going to need to, an important part of science is peer review. You republish papers. Those papers are written. You have to write them. So we need to sort of teach them how to take their big idea, their big discovery, this thing they know about the world, about which they could, write 10,000 pages and speak for 5,000 hours, and just compress it down to something that is understandable, but still has the sort of weight of the authority of the evidence itself, not of you as an authority figure, but at least some sort of feeling they can trace along, like tracing along on a map of how the evidence led you this way, even if they haven't done the experiments themselves. So I think that's a quite an important part of it, of when you've got a lot to say, how to be succinct and how to, the curse of knowledge, how to write to someone who doesn't know as much as you do, rather than in that English exam where you're writing to your teacher who knows a lot more than you do, and you have to try and fool them into thinking you know what you do. Apart from that, we're also going to teach them a bit about sort of talking about the scientific method. It's important that they, as well as be able to present the evidence, be able to talk about what science is and what it does, what makes it different from engineering and from history and from philosophy and from politics and all those sorts of things, what makes science science. And I think an important part of that is so that they know when they're in the scientific ballpark and when they're not. So if I say, the Earth is getting warmer because of CO2 emissions, I've made a scientific claim. If I say, therefore, we should cut out all CO2 emissions, I made a political claim. That's not a scientific claim. It's about what we should do. Now, that should be informed by the science, but science can't make that claim. That's us. We've got to make that claim. Maybe we see all the Earth getting warmer, and we're like, we're fine with it. That's just a decision we have to make. And so I think part of the reason why this climate change debate got so politicized, whatever side you're on, is that people forgot that distinction. And so it looks like the climate, from one side, you could paint all the other side as being entirely political. So I think that's an important sort of part of being scientifically literate, of being able to explain what science is and why it does what it does.
So that's a nice segue, actually, in terms of finding a way of encouraging our students what they need to do if they're thinking about a career in science, thinking of doing at least a degree in science. If you had an opportunity to share with Year 11 and Year 12 students in terms of, they're thinking about science careers, they're thinking of studying science further, what advice would you give them?
So I think, how do you know whether you should do a science degree? Part of what drove me was the feeling that in high school you were sort of getting the neatly packaged little part of the story, and I felt that you feel that in all of the the high school. So I almost went and became a lawyer. So I did legal studies in high school, and if I'd gone that way, part of the thing that would draw me in was the fact that I wasn't going to read like the legal studies textbook, that we're actually going to read, the law and cases and actually get to the front line, get to the point where I'm not relying on someone else for my information. I actually know where we are. And I think in science, one of the things that I really, really loved about finally getting to university and starting to study physics was the feeling that I was getting towards the front line. I was getting towards the point where I wasn't reading the simplified, easy version of this. I was getting to the real stuff. This is what the real scientists use. This is where the evidence is. And, the feeling that actually some of this, that getting to the point where the picture itself is starting to get incomplete. There are holes for someone to fill in, to go and learn more about the universe and fill in that detail in our knowledge of the world. And I think if you feel that drive, then university is going to scratch that itch. You're going to get to, a great big dose of the real stuff of science, of seeing the way it's done and doing research projects with real scientists and getting handed a whole bunch of real data that came from a real telescope that no one's looked at before, and now it's yours. So you go and see what you see and analyze it and see what comes out. So I think that for me was a sort of driving force. I'm sure loads of other people have loads of other reasons why they wanted to get into science, but for me that was an important one. You get a very broad set of skills, I have to say, if you're worried about things like employability. And we'll teach you proper data analysis and all those sorts of things. So yeah, those are very widely applicable skills. But in terms of, I really think, worry about that stuff later. Your university degree, if you've got a passion for a topic that you really want to get deep down into, then go and get deep down into it.
So now a little bit of a lighter side question. If you were in a mixed company, what's the stuff at the moment you really love talking about? What are you nerding about at the moment?
Oh, that's good. The thing other than my job that eats a nice amount of my time and budget is there are currently, I think, 11 musical instruments in this room. So that's my deep, dark, dirty secret. There's a ukulele bass just there, and a whole bunch of others around. Oh, there's a guitar just there, and there's a whole bunch of other ones around. So I'm actually, getting cello lessons and all this sort of stuff. So yeah, that's I've always been that way inclined, and finding a way for that to sort of release itself in my spare time has been a whole lot of fun, and not a lot of fun for my family, who've got to put up with me. Certainly, I've been playing now for a couple of years on the cello, and the first year I was ready for it because I know what it takes to learn a new musical instrument. But boy, it sounds terrible. The violin is worse because it's high and scratchy, but the cello is not great when it's. At one point, I was trying to play, I think it's My Bonnie Lies Over the Ocean, and played like horrifically the first line, and just heard my wife killing herself laughing in the kitchen for very good reason, because it was awful.
Teach us something about that, maybe something that we don't know about, I don't know, cello music or about ukulele basses. Tell us something that, we'll like, oh, I didn't know that.
Well, I mean, Geraint and I have a Alas, Lewis and Barnes, our little sort of thing that we do on YouTube. And I chatted to him. I convinced him we should do a music and physics thing, because he's not musical at all. Although he apparently just loves singing. And as a Welshman,
in Welsh.
He's a disgrace to the Welsh singing tradition. So we did a sort of, I tried to explain the physics and the mathematics of music. It's, if you've got that mathematical brain to any sort of degree, there's a whole bunch in mathematics that you can just get your head, get your head into very nicely. So one of the things I've been learning actually is I recently, just at the end of last year, upgraded my cello from a thing that my wife bought me for $50, which there's a great YouTube channel. I think it's called Olaf the Violin Maker, and he calls these cheap $50 violins violin-shaped objects, VSOs, and so that's a cello-shaped object. But I'm going to go a proper, I won't say the price, cello, and the difference in just resonance is amazing, because if you build this thing, so that's a bass guitar just there. There. In a bass guitar, it's the string that's vibrating, and you have a pickup which picks up the string. So especially in a big bass guitar, it's the string that where the sound is, and that gets amplified. With a cello, the string is vibrating, which makes the bridge vibrate, which makes the whole body of the cello vibrate. It's got that whole big thing. And so the thing you hear is the whole instrument. And there's a massive difference between having the $50 cello-shaped object where you play the note and it enters the cello, and the cello doesn't quite know how to vibrate in the right way to make it sound the same. So you have resonant vibrations in any object. So in a glass, especially in a wine glass, if you set up the right vibrations, it'll ring. And if you don't set up the right vibrations, it'll just sort of fight against itself. The wave bouncing off this side and the wave bouncing off that side will sort of interfere with each other, and it won't quite. And so the cello-shaped object, you're constantly fighting against it. You're trying to put a note in there that it doesn't want. Whereas the proper thing, the real thing, you play it, and it's like there's a choir in there that you drown out. Suddenly you play an A, and it knows what to do with an A. It knows how to vibrate like an A. And so this A comes out that's so much richer and louder and more substantial than what comes out of the other thing. And so to feel that, especially because in a cello it's up against your chest, right, when you're playing. So just the applied lesson in the physics of resonance and vibrations and all that stuff has been fantastic. So so I've been loving all that stuff. Behind me, I think it's that book there, is a book called The Physics of the Theory and Practice of Piano Tuning. So I read a great big book on that because it sounded interesting. It's all really fascinating stuff.
It's a real nice synergy between two what can sometimes be thought of as almost mutually exclusive domains, music and physics, but you've got this lovely synergy here where you have a deeper understanding of what music is at the very fundamental level. I guess it enriches your music playing, and it also enriches your physics understanding as well, which is fantastic. It's fantastic. Yeah, that's excellent. Well, that's wonderful, Luke. Thank you for your time. It's been a really great discussion. I love what you've had to share, particularly in terms of your scientific literacy and teaching our students to communicate their knowledge better. And I think that's been helpful. And I certainly enjoyed your music as a lover of music, and having used to play piano and trombone myself, I know exactly what you're talking about, and it's a nice thing to share. And it's great. Has Geraint tried to teach you some Welsh as you try to teach him some music?
He doesn't. He knows bits and pieces of Welsh, but isn't actually fluent. Although we did, when I finished my music rant, we sort of went, we should find some other topics that because he knows a bunch of stuff about. He's very, there's other things he's very into. So, maybe I can coax him to start up about one of those.
I'm looking forward to the next video where we have a duet with his Welsh singing and your cello. I think there'll be a sight for sore ears.
We were in middle of 2019. We're in Croatia, which was very nice, at a conference at the same place, and he got a song stuck in his head and just sung it the whole time. It's terrible. Anyway, I shouldn't slag him off too much.
No. Are you guys writing another book?
We have some plans, yeah. We have some ideas about what to do next. There's a couple of things on the front burner and a couple of things on the back burner, and hopefully we can get into that, because we certainly both want to write some more. So
yeah. Well, I'll make sure I put the link to your YouTube channel in the description for those who want to hear it. And for those who are listening on the podcast, I'll check out my Physics High website, and I'll make sure that link is somewhere particularly in line with the podcast that you are hearing. Dr. Luke Barnes, thank you for your time, and appreciate what you've had to share. And hopefully an opportunity to speak more in the future on other astronomy topics. Thanks again.
Thanks for having me. Thanks.
Well, I hope you enjoyed this episode. Please subscribe to get notifications of up-and-coming interviews, as well as my other physics content. My name is Paul from Physics High. Till next time.